Welcome! Get ready to embark on a fascinating journey. Today, we're diving into the hidden world of digital signals. It's a realm that underpins almost everything we do with technology. We'll explore how information is encoded, transmitted, and ultimately, how it shapes our digital experiences. That song you're streaming? Think about it for a moment. It's not a smooth wave, the continuous flow of sound you might imagine. Instead, it's thousands of tiny snapshots per second, discrete measurements capturing the sound's intensity at specific moments in time. This process is called sampling, and it's the foundation of digital audio. Think of it like a flipbook, a series of still images. Each page is a data point, a single frame of the action, and together, when flipped rapidly, they create the illusion of continuity, of smooth, flowing motion. The same principle applies to digital signals. This is a discrete time signal, the language of all modern tech. From your smartphone to your smart refrigerator, everything relies on this method of representing information. It's the common thread that ties our digital world together. Digital photos work the same way. They are also built upon discrete data points. Zoom in and you'll see millions of pixels, each with its own color and brightness. These tiny squares are the building blocks of the image, each holding a specific piece of information. Your computer sees images as grids of numbers, not sunsets. It interprets the numerical values associated with each pixel to recreate the scene. Why break things into pieces? What's the advantage of this approach? Control and precision. That's the key. Analog signals are messy and hard to copy. They are susceptible to noise and degradation. Digital signals are just numbers, easy to store, in memory or on a hard drive. Copy and manipulate. You can edit, enhance, and transform digital data with incredible accuracy. Send a list of numbers across the internet through cables and wireless connections, and you get a perfect replica on the other side. No loss of quality, no distortion. Our brains smooth over the gaps, filling in the spaces between the data points, so we hear melodies and see clear images, not individual data points. Our perception bridges the digital divide. This is the magic of digital media, the seamless experience we enjoy every day. Breaking the world into numbers, a process of abstraction and simplification, then letting our minds put it all back together, reconstructing the original experience from these digital fragments. Understanding this is the first step to unlocking how our favorite tech works. It's the key to demystifying the digital world around us. Let's see how we decode these numbers and delve deeper into the fascinating world of digital signals. We have all these numbers, but what do they mean? Enter the discrete Fourier transform, or DFT, a mathematical decoder ring for digital signals. Imagine an orchestra. You hear a complex sound, but the DFT lets you pick out each instrument. It breaks a signal into its basic frequencies, showing you the ingredients inside. This makes editing, filtering, and compressing signals much easier. Want more bass in a song? The DFT shows you where to boost. Equalizers, compression, and noise reduction all rely on this. The DFT changes our perspective, letting us see signals as collections of pure frequencies. It's the key to understanding and manipulating digital information. Let's dive into a practical demonstration and see the discrete Fourier transform, or DFT, in action. We're going to walk through a simplified example to illustrate how this powerful tool works. We'll use a simple example to keep things clear and easy to understand. This will help solidify the concept. Imagine we have a digital signal represented by just 4 samples, 4 discrete points in time. These samples capture the essence of a signal at specific moments. Let's say those values are 20 minus 20. These numbers represent the amplitude of the signal at each of our 4 sample points. If you were to plot these points and connect them, it would start to look like a wave, a repeating pattern. But what kind of wave is it? What frequencies are present in this signal? That's the question the DFT helps us answer. The DFT works by comparing our signal, the one we're analyzing, to a set of standard test waves. In this case, since we have 4 samples, we'll compare it to 4 standard test waves. These waves represent different frequencies. The first test wave is a flat line representing a DC component or a frequency of 0. The second is a wave that goes up and down once within our 4-sample window, representing a low-frequency oscillation. The third does it twice within the same window, representing a medium-frequency oscillation. And finally, the fourth is the fastest possible wave that can be represented with only 4 samples, representing the highest frequency our system can detect. When we compare our signal to these test waves, we find that it matches the second wave, the one that goes up and down once, perfectly. Therefore, the DFT tells us that this second frequency is the main ingredient, the dominant component of our signal. The other test waves, the flat line, the wave that goes up and down twice, and the fastest wave, don't match our signal at all. Because they don't match, their corresponding DFT outputs are zero, indicating that these frequencies are not present in our original signal. So, what's the result of this comparison? A new set of 4 numbers, representing the strength of each frequency component. These numbers show us the strength or amplitude of each of the 4 test frequencies within our original signal. In this specific case, the DFT outputs are 0, 4, 0, 0. This means there's 0 strength in the DC component, a strength of 4 in the second frequency, and 0 strength in the third and fourth frequencies. With these 4 numbers, we've effectively decoded the signal, breaking it down into its constituent frequencies. We can see that it's made almost entirely of one frequency, the second one indicating a clear and dominant wave pattern. This simple example illustrates how the DFT reveals the hidden structure, the underlying frequency components inside any digital signal, no matter how complex it may seem. And the beauty of it is, there's no scary math required to understand the basic principle. At its core, it's just pattern matching, finding the best fit between your signal and a set of known frequencies. That's the power of the DFT, its ability to decompose complex signals into simpler, understandable components. But there's a catch. While the concept is simple, the actual computation can become quite intensive, especially for long signals. The discrete Fourier transform, or DFT, is an incredibly powerful tool in the world of signal processing. It allows us to analyze the frequency components of a signal, which is essential for countless applications. But, and this is a big but, it's also notoriously slow, especially when dealing with large data sets. The computational burden can be significant. For a small number of data points, say just 4, the DFT is relatively easy to compute. The calculations are straightforward and can be done quickly. But as the signals we're analyzing get longer and more complex, the number of calculations required by the DFT increases dramatically. The computational demands explode exponentially, quickly overwhelming even powerful computers. The DFT's workload doesn't just grow linearly, it grows with the square of the number of samples. This is a crucial point to understand its limitations. N squared. This quadratic growth means that doubling the amount of data quadruples the computation time. Consider just 1 second of CD quality audio. That's 44,100 samples that need to be processed. Performing a DFT on that data requires nearly 2 billion calculations. The numbers quickly become astronomical. So what about real-time processing? Forget it, it's simply not feasible with the standard DFT for many applications. Your device would either lag unacceptably, struggling to keep up with the calculations, or it would overheat due to the intense processing demands. This inherent slowness made the DFT largely impractical for many real-world, real-time applications where speed is paramount. Applications like video calls, which require immediate processing of audio and video data, or image processing, where filters and effects need to be applied quickly, and even streaming services, which need to decode and display video in real time, were all effectively out of reach due to the computational limitations of the DFT. Engineers and scientists had the theoretical understanding of how to use the DFT, but they lacked the computational speed necessary to make it truly useful. In a way, the DFT was like a high-performance race car sitting in the garage with no fuel. It was an amazing tool in theory, full of potential, but stuck in the garage in practice, unable to be used to its full capabilities. The world desperately needed a breakthrough, a way to overcome this computational bottleneck. We needed a method that could deliver the same accurate results as the DFT, but much, much faster. And that's where the hero of our story enters the stage, the fast Fourier transform, or FFT, a revolutionary algorithm that changed everything. In 1965, James Cooley and John Tukey changed everything. They needed to analyze seismic data quickly. DFT was too slow. Their solution? The fast Fourier transform, or FFT. The FFT avoids redundant calculations by breaking big problems into smaller ones, then combining the results. It's divide and conquer for data. Their algorithm made frequency analysis practical for real-world use. Suddenly, problems once impossible became solvable. The FFT unlocked the true power of digital signal processing. How does the FT work its magic? Imagine building a 1000-piece Lego set. The DFT tries every connection. The FFT splits the task into small, manageable chunks. By breaking the problem down and reusing calculations, the FFT slashes the workload. For 44,100 samples, the FFT needs about 660,000 calculations, thousands of times faster than the DFT. This speed made real-time audio, video, and image processing possible. Video calls, instant photo filters, and streaming all became reality. The FFT didn't just speed things up, it made the digital world possible. It turned massive data problems into everyday tasks. Our devices use it millions of times a day invisibly. The data beast was tamed. Let's compare the DFT and FFT. The DFT is slow, n-squared complexity. Double your data, quadruple the time. The FFT is fast, n log n complexity. Double your data, just a bit more time. For small data, the difference is minor. For real-world data, FFT wins by a landslide. Remember, FFT isn't a different transform. It's a smarter way to compute the DFT. Both give the same result. FFT just gets there faster. Before FFT, DFT was mostly theoretical. FFT brought frequency analysis to everyone: engineers, artists, doctors. DFT is the what, FFT is the how. The FFT made the digital revolution possible. Without it, instant communication and streaming wouldn't exist. FFT is the unsung hero of modern tech. The FFT is everywhere, powering the tech you use daily. Music streaming? FFT compresses audio, making files smaller without losing quality. JPEG and MPEG? FFT helps compress images and video. MRI scans? FFT turns raw data into detailed images for doctors. Wi-Fi and 5G? FFT enables fast, reliable data transmission. Astronomers use it to analyze starlight. Engineers use it to check bridges. Even apps like Shazam use FFT to identify songs in seconds. The FFT is the invisible engine behind streaming, communication, medicine, and more. It's a silent workhorse, running millions of times a day. Without it, our digital world would grind to a halt. The FFT truly powers our connected lives. We've journeyed from digital signals to the FFT, the algorithm that changed everything. This story shows how a clever mathematical idea can transform the world. Math isn't just rules, it's a creative tool for solving real problems. Cooley and Tukey didn't invent new hardware, they found a smarter way to calculate. Their insight unlocked entire industries' music video communications. The lesson? Logical thinking and problem-solving are superpowers. The world is full of slow, inefficient systems waiting for the next FFT. When you face a tough problem, see it as training for your brain. You're learning the skills that built the modern world. Maybe you'll discover the next big breakthrough. The power to change everything is within your reach. Thanks for watching.